Hi everyone, this is Mrs. Jackson. This is Chapter 4, Section 3. In this section, we're going to be talking about variations. And just a reminder that I reordered the textbook section. So this is actually Section 1 in the textbook. And the only thing that the textbook goes over is inverse variations. And that makes no sense to me. So I'm going to, in this section, go over direct, inverse, joint, and combined variations so that you can get a feel for how they compare and contrast. And we're going to look at that in tables, graphs, and equations. So what is a variation? The key concept here is that a variation, first and foremost, is an equation. And that equation relates two or more variables through the operations of multiplication and or division. All right, so the first variation that I want to go over here today is direct variations. Another phrase that you might hear used is proportional. So if you see proportional variations, they are the same thing as direct variations. And direct variations are equations that have two variables whose quotients are constant. And one thing that can cause some confusion with students is a lot of students view linear functions, all linear functions, as direct variations, but actually only linear functions whose graphs pass through the origin are going to give you quotients between the output and the input that are constant. One of the most common direct variations is the distant rate time formula. This is a formula that we use to understand how much distance is traveled when something is in motion in a constant rate. So that formula I'm sure you've seen before in your life. It's d for distance equals rate times time. So for example, if a person is walking at a constant rate 3 miles per hour, we could model that as distance equals 3 times t. So if that person, and by the way, the units have to be are harmonious. For example, if the rate is in miles per hour, then the time has to be in hours. So if a person walked for 1 hour, obviously they traveled 3 miles. If a person walked 2 hours, they traveled 6 miles, etc. All direct variations can be modeled in a generic way as y equals k times x. So if I zoom in here, of course, this y is our output, and x is our input. And it's difficult for me to write, but this k is lowercase, and k is the constant of proportionality. So the way we would read this in English here, this y equals k times x, the way we read that is y varies directly as x. So if you saw that written in a sentence form, y varies directly as x, you would translate that English into this equation. As mentioned previously, the test for a direct variation is that their quotients between the output and the input is a constant. So you can see that right here in this equation. So y equals k times x. If I divide both sides by x, in other words, solve for k, our constant equals the quotient of the output to the input. So we're asked to determine whether or not something is a direct variation. Our test is going to be looking for that constant of proportionality. For example, in this data table, I have a set of coordinate pairs. I'm going to look to see, do I have a constant? Is my output divided by my input a constant? And here, 1 divided by -4 is -1/4. 3/4 divided by -3 is also -1/4. A half divided by -2 is also -1/4, etc. Now we do have one little gotcha in this table, and that is any number divided by 0 is undefined, but this still results in a direct variation. So the conclusion here is yes, this is direct. So what does this look like when we graph it? So if I graph these ordered pairs, -4 on the input, I have an output of 1. I'm going to have to move over here at -3, I have an output of 3/4, -2, a half, -1, a quarter, and finally at the origin. So you can see right away that it's a direct variation is definitely linear when graphed. However, if we had a different y-intercept other than the origin, it would not meet the test of having a constant of proportionality. So it has to go through the origin. Now, one thing I will note before we move on is that virtually every website out there, when talking about a direct variation, will describe it to the effect that when the input increases, the output increases. When the input decreases, the output decreases. In other words, they follow each other. And while that certainly is true for positive numbers, I picked this particular example to show you that it's not always true. So if you look at our input's increasing. It's going from -4 up to 0, so that is increasing, while our output is decreasing. So I just wanted to point that out. Most websites have that wrong. It's kind of a misnomer that they say that. And so I wanted to save you some potential confusion there. Okay, well, the second type of variation is called inverse variations, and you will also hear that referred to as indirect. And the key concept here is that if you have an inverse variation, it's an equation that have two variables whose products are constant. So unlike the direct variation, whose quotient is a constant, in this case, the products are constant. One potential example here that I've given you is the amount of time it takes the ice to melt varies inversely with the air temperature. So just kind of think about if it's warmer out, then ice is going to melt faster. If it's cooler out, ice is going to melt slower. So we could take these words, these varies inversely here, varies inversely, and we can write a little model here. So the time it takes is going to vary inversely with the temperature. And you can see instead of being k times the independent variable, this time k is being divided by the independent variable. So generically, if we wanted to generalize, we could write all inverse variations as y equals k divided by x, where y again is our output and x is our input, and lowercase k is our constant of proportionality. I didn't leave enough room here for this big word. Okay, and like we looked at with the direct variation, if I solve this for k, I'm going to undo that division of x with multiplication of x, and I'm going to see that the product of our output and input is going to give us our constant of proportionality. And the way we would read this in English is y varies inversely as x. So if you saw anything written like that, you would directly translate that into y varies inversely as x. Another phrase you might also read in a paragraph would be indirectly. So if you saw indirectly, you would translate in the same way. All right, so just as we did with direct variations, we're going to look at a set of data and determine if it's inverse or direct, and we will do that by solving for that constant. So if I have k equals the product of x and y, here I can see that 2/10 times 10 is 2, 4/10 times 5 is 2, 8/10 times 2.5 is 2, etc. And so, yes, this is inverse if I see that constant all the way down. Now let's take a look at how this appears in graphical form. So at an input of 2/10, I have an output of 10 and 5 and let's see, 8/10 is 2.5 and 1 is 2. 1 6/10, I'm down to 1 1/4, and at 2 I'm at an output of 1. So you can see very quickly that this is not linear. This is the opening of our chapter 4, this inverse variation, because this is the most basic of rational functions. It's called the reciprocal function, which we're going to be studying in the next section in depth. But that's why they open up this chapter with inverse variations. And to close out this topic, I wanted to just quickly talk about joint variations and combination variations, because you could see these on a SAT question. So key concept, joint variations are just like direct variations. The only difference is that they have more than one independent variable. So an example, the area of a triangle can be found using area equals 1/2 base times height. If we wanted to generalize here, I could write a joint variation as y equals our constant of proportionality times 2 independent variables. So y is our output, k is our constant, and x and z in this case are inputs. So in English, this would directly translate as y varies directly with x and z. And finally, combination variations is exactly what your intuition would tell you. So a combination variations combine both direct and inverse. So in the following example, there's actually a typo here. So y varies jointly with x and z and inversely with r squared. So you would translate that as y varies jointly with x and z. So you have your constant of proportionality. X and z would be multiplying that constant. And inversely then, r squared would be in the denominator. All right, so in this video, we talked about 4 different types of variations: direct, inverse, joint, and combination variations. I hope this video helps. Thanks for listening.